This lesson is going to cover a bit of a potpourri of topics in solutions. We're going to look at the solution process and some of the factors that affect solubility. We're going to examine concentration units in greater detail than what you know already. And we're going to start with a short introduction of colligative properties. When we're looking at the dissolving of a substance, of a solute in a solvent, and we want to look at whether or not the substance is going to dissolve, we need to think about the solution process in greater detail. When a solute is dissolved in a solvent, although you might think of it as a one-step process, the solute dissolving, there are actually three steps if we look at it in a thermodynamic, more detailed way. In order for a solution to be created, what ultimately we need is for the solvent particles to interact with the solute particles. Before the interaction can happen there, we need to first break up the solvent particles. And this is an endothermic process. We need to separate the solvent particles to make space for the solute. In addition to that, in preparing to dissolve, the solute particles need to be separated as well. And this also is an endothermic process. The third step in the solution process is creating an interaction between the solvent and the solute particles. This is an exothermic process. So what this means when we consider the three steps is that sometimes when we dissolve a substance, the overall reaction is going to be endothermic, so the temperature drops. In other cases, the overall process might be exothermic and the temperature might rise. Whether it's endothermic or exothermic will depend on the heat released or absorbed in each of the three steps. So we need to consider them all together. Now when we study thermodynamics later, what you'll learn is that there are two parts of a solution, forming a solution that might be favorable. If it's an exothermic reaction that's produced, then that is a favorable process. But also, one of the energetically favorable parts of forming a solution is that a solution has greater disorder. This is called entropy. So the solvent particles are relatively organized. The solute particles are relatively organized. But when we have a solution, we have much more disorder. Disorder is related to the possibilities of organization. So there's much more options for how this solution is organized. When we look at the factors that affect solubility, there are a few things to consider. First of all, the polarity of the two substances, the solute and the solvent, must be considered. So we have this little phrase, like dissolve like. So nonpolar molecules are insoluble in water, for example, because water is a polar substance. Nonpolar molecules will better dissolve in nonpolar solvents. When we're talking about the solubility in water, we can also consider whether the substance can form hydrogen bonds with water. So something like ethanol or methanol that has an OH bond in the molecule, it has the ability to form hydrogen bonds with its own type of molecule, but it can also form hydrogen bonds with water, which makes it soluble. The greater the chance or opportunity for interaction, the more soluble it's going to be. For ionic compounds dissolving in water, as you know, ionic compounds tend to dissolve in water, partly because of the interaction between the polar water molecules and the cations and anions of the ionic compounds. As you know from your studies of solubility, not everything has the same solubility, and there's a few factors that are present to consider to help us to decide whether or not something will actually be able to dissolve in water. One thing to consider is the size of the ions. Smaller ions are going to be less soluble. And this comes from the fact that the smaller the ions, the more difficult it's going to be to break apart the solute particles. Okay, so this step of breaking up the solute particles is important to consider when we're studying the solubility of ionic compounds. We know that this step is going to be favorable no matter what for an ionic compound because we have a positive and negative ion interacting with the polar water molecules. So really, when we're comparing the solubility of ionic compounds, we're looking at how difficult it's going to be to break apart the solute particles. And what we're breaking here is what is called lattice energy. It's the energy holding the ions together. So the smaller the ions, they're packed much more efficiently and they've got a stronger lattice energy. Therefore, they're more difficult to break apart, which leads to a lower solubility. The other thing to consider is the charges on the ions involved in the ionic compound. So if you're comparing something like calcium chloride and sodium chloride, the greater the charges, so calcium has a 2 plus charge and sodium has a 1 plus charge, the calcium has lower solubility because the ions are much more tightly held together. Okay, so the smaller, more highly charged have a greater lattice energy. Therefore, breaking apart the solute particles is more difficult and it lowers the solubility. In your note, you have a chart that compares these compounds to one another. Okay, and we're looking at comparing their solubility. You have numerical values to compare the solubility, and so what you can see is that the CaF2 is the lowest solubility, okay, and the consideration here is the charges, okay, because calcium has a 2 plus charge. Okay, we're also dealing with the smallest ion of fluorine compared to the other halogens. For these four substances, they both involve a positive and negative ion. Okay, so the charges will not affect the solubility. Here it is the size of the ions that will have an impact on the solubility. So fluorine, being the smallest ion out of the four, okay, is going to have the strongest lattice energy, and so it's going to have the lowest solubility. When we're studying solutions quantitatively, we've got our concentration units. Okay, you can look at a solution in its percent by mass, so the mass of the solute over the mass of the solution. You're very used to dealing with molarity, which is the moles of solute per liter of solution. Okay, there should not be a times 100 here. Apologies, take that out. What we're going to do now is look at molality, which has a unit of lowercase m, and it is the moles of solute per mass of solvent in kilograms. This is a new unit of concentration that we're going to use to study some of the properties of solutions. And the reason that we need to consider this unit in some cases over molarity is that when we're considering molality, it's not going to be temperature dependent. So if we change the temperature of a solution, the molality is not going to change because the mass of the solvent will not change. With molarity, what we need to consider is that when we heat up a solution, the volume might change, even if ever so slightly, it could change, and so the molarity would actually change with it. So when we're studying properties over a range of temperatures, which we will be doing, we need to use molality in our studies. Density is the property that connects the two units. So what we're going to do is look at converting between molality and molarity in both directions. We're also going to do a couple of examples of calculating molality from a given scenario. In this example, molality going to molarity, we've got a 0.396 molal glucose solution with a density of 1.16 grams per milliliter. And we want to find the molarity. So we want the moles per liter of solution. It's a three-step process. The first thing that we need to do is actually figure out what the mass of the solution is. Okay, so the mass of the solution, it has two parts. The mass of the solution is the mass of the glucose that we have plus the mass of the solvent that we have. In a 0.396 molal solution, what this is 0.396 moles per kilogram of water. And there's a kilogram of the solvent was used to prepare the solution. So if we want to figure out the mass of the solution, the mass of the solvent is easy because we're given the molality, so we've got 1,000 grams of solvent, or 1 kilogram of solution. For the mass of the glucose, we know that we've got 0.396 moles of the glucose, so we're going to multiply by the molar mass of glucose, which is 180.2, and we're going to find that we've got 71 grams of glucose. So the mass of this solution that we're dealing with is 1,071 grams. Because we know the density, we can find the volume of the solution by taking the mass and dividing by the density. Okay, so when I say that the density is the linking variable between molarity and molality, this is what I mean here. Okay, so we've got 923 milliliters of solution using the density and the mass, which is 0.923 liters of solution. So now I'm prepared to find the molarity, or the concentration. The moles that I have is 0.396, and I've got 0.923 liters of solution. So the molarity of this solution is 0.426. Okay, so it's really important, okay, to recognize that molarity, which is moles per liter of solution, is big M for its unit, and molality is moles per kilogram of solvent, and it's lowercase m for its unit. Okay, we can also go the other direction. So if we're given the molarity, we can find the molality. Again, the density is required in order to complete this calculation. Okay, this is actually incorrect. Okay, we're also going to need the molar mass of sodium chloride, so I'll just write it up here. So what we need to do if we want to convert from molarity to molality is we need to first figure out the mass of the solution. Because remember that molality is the moles per kilogram of solvent. So ultimately we need the moles of sodium chloride that we're dealing with and the mass of the solvent. So if we find the mass of the solution, okay, we know we've got 1 kilogram. Okay, sorry, we've got 1,000 milliliters of solution, okay, because we've got a 2.5 mole per liter solution. So that's 1,000 milliliters. From the density of 1.808, okay, we can figure out that the mass of our solution is 976 grams. This is the mass of the solution, which includes both the sodium chloride and the solvent. So what we need to do now is actually figure out what portion of that is the mass of the solvent. We know that we've got 2.5 moles of NaCl. So using the molar mass, multiplying by the molar mass, we determine that we've got 146.1 grams of NaCl. The total mass of the solution is 976. The mass of the sodium chloride is 146. So we can determine the mass of the solvent by finding the difference, which is 829.9 grams. When we're dealing with molality, we need the mass in kilograms of the solvent. Okay, so it's 0.829 kilograms. So now we've got the moles of sodium chloride at 2.5 in 0.829 kilograms of solvent. So the molality is 2.5 divided by 0.829, and we've got a molality of 301. Couple more examples here. We want to know the molality of a solution prepared by dissolving 4.3 grams of sucrose in 676 grams of water. So you can imagine preparing this solution. It would be different. You're not using a volumetric flask here. You're actually using a scale to measure 676 grams of water and measure 4.3 grams of sucrose. Okay. If you want the molality, you are looking for the moles per kilogram of solvent. So we need to figure out the moles of sucrose that we have. By taking the mass and dividing by the molar mass. So in this solution, we've got 0.04164 moles of sucrose. So the molality, which is the moles per kilogram of solvent, is 0.04164 divided by 0.676. You simply need to convert the grams of the solvent to kilograms by dividing by 1,000. So we have a molality here of 0.616. And the way that we express that is it's a 0.0616 molal solution. Just like capital M was molar, for molality we use the term molal. So we've got a solution here. We want the molarity and the molality for this solution prepared by dissolving 30 grams of NH3 in 70 grams of water. To calculate the molarity, we actually need the volume of solution. So that's why the density is given. The volume of the solution is the mass divided by the density. So the mass of this solution, okay, when we consider the mass of the entire solution, we need to take the total, so it's 100 grams, and the density is 0.982. So you've got 101.8 milliliters of solution. We're also going to, for both cases, need to know the moles of the solute, which is the NH3. So we've got 30 grams of the solute. The molar mass of NH3 is 17.04. So we've got 1.761 moles of the solute. So to find the molarity or the concentration, we're going to take these moles, 1.761, and we're going to divide by the volume of solution in liters. So divide by 1018, and we find that we've got a 17.3 molar solution. For the molality, it's the moles of the solute, 1.761, divided by the kilograms of solvent, which is 0.07, because I've got 70 grams of water. So the molality of this solution is 25.2. You're going to see that we use molality when we study solutions and the properties of freezing point depression and boiling point elevation, which will be our next lesson. Now, the last major topic in our study of advanced solutions is colligative properties. And colligative properties are ones that depend not on the identity of solute particles that are being dissolved, but on the number of solute particles that are dissolved in a solution. So properties that are colligative properties are vapor pressure, freezing point, boiling point, and osmotic pressure. So what you're going to find is that when you're studying these properties, they are affected by solute being added. Okay, so the vapor pressure of something is affected when we add solute. The freezing point or the boiling point are affected when we add solute to a substance. But we don't concern ourselves with what the solute particles actually are, rather how many of the solute particles have been dissolved. So one of the key considerations of this is the differentiation between molecular compounds and ionic compounds. So a molecular compound that doesn't dissociate or break up into ions will have a 1-to-1 ratio. So the number of molecules that you put into the solution is what you're going to consider when you're looking at the effect on these properties. For ionic compounds, since they dissociate, we need to consider the ratio that they dissociate in. So something like sodium chloride, which dissociates into Na plus and Cl minus, for every 1 mole of NaCl, you're putting 2 moles of solute particles into the solution. Something like calcium chloride, for every 1 mole that you dissolve, we actually put 3 moles of solute particles into the solution. Okay, so this is going to be a major factor when we are studying colligative properties. Now you'll recall from last year that you studied phase diagrams. Okay, so they give you the relationship for a particular substance between pressure and temperature, and we can look at the different phases. So for a given pressure and temperature, you can identify whether the substance is going to be a solid, liquid, or gas. And you can also identify phase changes and the temperatures and pressures of the phase changes. Okay, some key points here. The triple point is where all 3 phases exist. Okay, and then the normal boiling point or the normal melting point are the temperature of these phase changes at 1 atmosphere. Okay, so that's going to be a key term that you're going to be using as we move through the rest of this unit. Now, a property that you discussed last year, okay, when considering intermolecular forces and the properties of substances, was vapor pressure. And when you were looking at it last year, you talked about whether or not something would be expected to have a high vapor pressure or a low vapor pressure, and it was related to the intermolecular forces of that substances. When you think about vapor pressure, what you need to consider is a substance like a liquid in a closed container. Naturally, the molecules in the liquid state will evaporate to the gaseous state at room temperature. Depending on the intermolecular forces, a different amount of molecules will actually escape. This eventually reaches an equilibrium. So if you think of the very first thing we talked about when we studied equilibrium was a closed container of liquid water. And you understand that water naturally evaporates, but in a closed container, it actually naturally condenses as well. Okay, so we can reach an equilibrium state between the gas and the liquid. The pressure of this gas, okay, so we think of this gas pushing on the outside of the container, the pressure of this gas that lies above the liquid is called the vapor pressure. What we're going to look at as a colligative property is the effect of adding a solute to a solvent on the vapor pressure. When you add a solute to a solvent, the vapor pressure is actually lowered. So what is actually happening is there are fewer molecules that are escaping the surface of the liquid and putting gas into the space above the liquid. So therefore, the vapor pressure, okay, the pressure of this vapor on the outside container is lowered. Now, the thermodynamic reason for this happening is that by allowing for greater disorder in the solution, the system isn't seeking the disorder by allowing vapor to be produced. So overall, it's satisfied with the entropy of the disorder from the solution. So fewer molecules are escaping the surface. Now the decrease in the vapor pressure is actually directly proportional to the amount of solute that is actually in the solution. And the relationship is here. So the new pressure is actually equal to the mole fraction of the solvent particles times the vapor pressure of the solution, of the pure solvent. Now let's look at an example here. Okay, say I had a substance that had a vapor pressure of 500 millimeters of mercury. So pure solvent, if I studied its vapor pressure, I would determine it to be 500. Okay. Now, if I create a solution that is actually 75% of the solvent, so I put in 25%. Okay, so if there's a mole fraction of solvent at 0.75, what I would actually find is that the pressure would lower to 375. So it's directly proportional to the amount of solvent. So if you've got 75% solvent in your solution, which is the equivalent of a mole fraction of 0.75, your pressure is going to be 75% of the pressure of the pure liquid. We can also consider the change in vapor pressure if we use the mole fraction of the solute present. Okay, so in my scenario over here, where I've got a mole fraction of solvent of 0.75, that's going to give me a mole fraction of my solute of 0.25. Okay, so if I take this, okay, the mole fraction of the solvent is 1 minus the mole fraction of the solute. And if I rearrange this and you follow the rearrangement, you can see that the change in vapor pressure, or the vapor pressure lowering, is actually equal to the mole fraction of the solute times the vapor pressure of the pure solvent. So if we use our example of 0.25, okay, you can see that delta P is 0.25 times 500, which is actually equal to 125. And this makes sense because if we look at our before and after, we started with a vapor pressure of 500, and it was lowered by adding the solute to 375. So the change in vapor pressure is 125. And we're going to look at another example in a few minutes. Now, this scenario here, okay, is where we're looking at a solute that's being added that is non-volatile. So it itself, it doesn't actually go into the vapor. In our second scenario, we're going to look at a solution that's prepared by mixing two volatile components. Okay, so both the solute and the solvent are able to evaporate or will hold their own individual vapor pressures. Okay, this graph here looks at a solution of toluene and benzene. And toluene and benzene, when they're combined as a solution, are considered ideal, okay, because they exhibit similar intermolecular forces. Okay, we're going to see the effect in a few minutes of a solution that's not ideal. The reason they have similar intermolecular forces is because their structures are very, very similar. Quantitatively, we're only going to be studying ideal solutions, or one where the intermolecular forces are similar. When we are looking at a solution that's prepared where both components are volatile, their individual vapor pressures are going to change as the mole fractions of these substances vary. Okay, so keep in mind that the mole fractions of these substances, so XA plus XB, will always equal 1. Okay, the vapor pressure of the pure liquid A and the vapor pressure of the pure liquid B are P naught A and P naught B. The total pressure of the system, as you know from Dalton's law of partial pressures, is going to be equal to the sum of the individual pressures. Okay, so let's look at a couple of points on here. So what you can see from this is if I've got a pure solution of benzene, so the mole fraction of benzene is 1, okay, the total pressure of the system and the partial pressure of benzene are equal, okay, and the pressure is at about 780. When we look at a solution that has no benzene in it, so it's purely toluene, the partial pressure and the total pressure are the same as that of the vapor pressure of toluene, which is approximately 300. Okay, so if we look at a scenario, so for example, where the mole fraction of benzene is 0.6, we can actually determine the total pressure and the partial pressure of each of the individual substances. So if the mole fraction of benzene is 6, then the pressure of benzene at that point is 0.6 times 780, which is 468. The partial pressure of toluene, which at this point has a mole fraction of 0.4, is 0.4 times 300, which is 120. Okay, so the total pressure at this particular point is 768 plus 120, which is 588. Okay, so the difference from scenario 1 to scenario 2 is we need to consider the change of the vapor pressure on each of the substances. Now let's consider just qualitatively a non-ideal solution. So this is a solution where we've got components A and B, but we have substances A and B that do not have similar intermolecular forces. There are two possibilities. We need to consider the force of attraction between A and B. If the force of attraction between A and B is less than the attraction of A to A, or the intermolecular forces of A, and the intermolecular forces of B. Okay, so if this is smaller, what's going to happen is when we combine A and B, the molecules are going to have a greater tendency to actually leave the solution. Because the forces of A to A and B to B are stronger, okay, and the A to B are weaker, when they're combined, there is a likelihood that the molecules will escape the solution. So what we have here is a higher than expected partial pressure of A, B, and therefore total pressure. More molecules escaping. You need to imagine that's going to increase the pressure above the liquid because there are simply more molecules above the liquid. Okay, so if we allow the molecules to escape by having a low attraction between the two, that's going to be a positive deviation from Raoult's law. In a scenario where the force of attraction between A and B molecules is actually larger, what that's going to do is actually enhance the attraction in the liquid when we combine the two substances. And what's going to happen is there's going to be less tendency for molecules to escape the surface of the liquid. And so we're actually going to have a negative deviation, okay, or a lower than expected vapor pressure of a combined solution. Okay, so this is the extent of the discussion for deviations from Raoult's law. You will not be doing calculations involving these because the calculations that you're going to do will always involve ideal solutions. Let's look at two examples of Raoult's law. Okay, one where we have a low volatility solid and one where we have a solution involving volatile solute and solvent. The vapor pressure of benzene is 100 millimeters of mercury at 26.1 degrees Celsius. Calculate the vapor pressure of a solution containing 24.6 grams of camphor dissolved in 98.5 grams of benzene. Camphor is a low volatility solid. Okay, so that's an important consideration. So you've prepared this solution. So in order to determine the new vapor pressure, okay, which is going to be the mole fraction of benzene times the vapor pressure of pure benzene, we need the mole fraction of benzene. So what we need is the moles of camphor, okay, and the molar mass of camphor is 152.26 grams. Okay, and we need the moles of benzene, okay, the moles we have is 1.261 moles. Okay, so from this we can find the mole fraction of benzene, which is the moles of benzene, okay, over the total moles. And a reminder that when you're looking at mole fraction, you can always think about it as the percentage before you divide by 100. Okay, so it's always the part divided by the whole. So the part that's benzene over the total amount of solution. Okay, so in this case, the mole fraction is 0.886. So the new pressure is 0.886 times 100, okay, which is 88.6 millimeters of mercury. And as expected, we have a vapor pressure lowering. In this last example, the vapor pressures of ethanol and 1-propanol at 35 degrees Celsius are 137.6 millimeters of mercury. We're going to assume ideal behavior, which means that ethanol and 1-propanol must have similar intermolecular forces. And we're going to calculate the partial pressures of each component of the solution, in which the mole fraction of ethanol is 0.3 atmospheres. And we're going to determine the vapor pressure of the solution. Okay, so first of all, this should not have a unit. So we've got the mole fraction of ethanol is 0.3. So because we know the mole fraction directly, we don't need to calculate that. And what we can find is the partial pressure of ethanol, which is the mole fraction of ethanol times its individual partial pressure at that temperature. So we've got 0.3 times 100, which is 30. The partial pressure of the propanol is the mole fraction of the propanol, which in this case is 0.7. And remember that the mole fractions will always total 1, okay, much like percentages will total 100. And the partial pressure of the propanol is 26.3. The units for both of these are millimeters of mercury, as given in the question. So the total pressure, using Dalton's law of partial pressures, is simply the sum of these two. Which is 96.3. Okay, so each individual substance has experienced vapor pressure lowering. And we've got the overall total pressure. So that concludes our discussion of vapor pressure lowering. The final lesson of this unit will be boiling point to elevation and freezing point depression, which are also colligative properties. And we're going to be using molality in order to do calculations in that section.